Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this lecture session. Today's topic is refrigerator and heat pump. This is the 17th module of the course Thermodynamics and its application. I am Subhasis Maji, professor in School of Engineering Technology from Indira Gandhi National Open University. So today's topic is refrigeration and heat pump. Let us begin our discussion. After listening to this video lecture, you will be able to understand refrigeration system, you will be able to know refrigerator and heat pump, you will be able to describe refrigerants. You will be able to explain the capacity of refrigerator and you will be able to calculate the coefficient of performance. First of all, let us discuss about the direct heat engine and reverse heat engine. In the direct heat engine, the engine takes the heat from a high temperature reservoir. We call it source, and for this case you see that Q1 is the heat received by the engine from the high temperature source, and engine performs work W, and Q2 is the heat rejected in the sink. We call it low temperature reservoir. But one thing you have to be very careful, that T1 is always greater than T2. That means the temperature of the source is always greater than the temperature of the sink. Now, the reverse heat engine, purpose of this reverse heat engine is we have to take the heat from the low temperature of reservoir and sending it to the high temperature reservoir. But as far as the Clausius statement, it says that it is impossible for a device working in a thermodynamic cycle to transfer heat from a low temperature region to a high temperature region unless and until we do some work. So if we want to transfer heat Q2 from the low temperature reservoir to a high temperature reservoir, we have to do some work, that is W is work input to the system. That is the purpose for this, and that is all about the reverse heat engine. Now let us talk about the coefficient of performance. Coefficient of performance of a refrigeration system is defined as the ratio of heat extracted in a given time, that is refrigeration effect, to the work input to the system. So COP is defined as heat extracted divided by the work done, or we can also say that COP of a refrigeration system is equal to the net refrigerating effect divided by the compressor work. We all know about different applications of refrigeration. Refrigeration is used for preserving fresh food, to store medicine, vaccines, blood, plasma. Refrigeration is also used to store cut flowers, to preserve. For ice plants it is used, and refrigeration system is also widely used in industries and also in manufacturing industries. And the refrigeration system is also used for chilling oil to remove wax in oil refineries. Now, when you want to purchase any refrigeration system or any air conditioning system, you have to tell that what capacity you would like to have that particular equipment. So, it is the rate at which heat can be extracted from cold body. That is the rate at which refrigeration can be produced. It is defined as the quantity of heat removed, that is refrigerating effect, to freezing 1 ton of water at 0 degree centigrade to ice at 0 degree centigrade in 24 hours. So 1 ton of refrigeration is the cooling rate equivalent to 12,600 kilojoule per hour, that is equal to 210 kilojoule per minute, that is also equal to 3.5 kilojoule per second. This is the block diagram of the refrigerator. In this case, you see that there are 4 important components. One is expansion device, second one is evaporator, third one is compressor, and the fourth one is condenser. Now, at the beginning of the evaporator system, the very cold refrigerant is entering into the evaporator, and you know very well that it will always transfer from hot body to the cold body. Since the refrigerant is very cold, that's why it will transfer from the confined space which is to be cooled inside the evaporator onto the refrigerant which is circulating in a coil inside the evaporator. So Q2 is heat extracted from the confined space which is to be cooled. Now, after extracting heat in the evaporator, the refrigerant will enter into the compressor, where work is to be done onto the system in the compressor to increase the pressure and temperature so that it can give out the heat while passing through the condenser. And Q1 is the heat given out by the refrigerant in the condenser, and after that, when the refrigerant will be in the liquid form, it will enter into the expansion device. Now, while passing through the expansion device, there is a sudden pressure drop, and because of the less pressure, after just passing through the expansion device, its temperature and pressure will decrease, and some of the refrigerant will start boiling and takes the latent heat. Thereby, the refrigerant will be at a very cold temperature, and then it will pass through the evaporator, and that's the way it completes the cycle. Now, the figure 1 shows the schematic of a domestic refrigeration system that operates in a thermodynamic cycle. The working substance that undergoes the cycle is referred to as refrigerant. Heat Q2 is transferred to the refrigerant in the evaporator to maintain at a low temperature. As a consequence of this heat transfer, the liquid refrigerant coming from the expansion device gets vaporized in the evaporator, and the low pressure, low temperature vapor leaves the evaporator to enter the compressor. Work WC supplied to the compressor from the electrical mains increases the pressure and temperature of the refrigerant vapor as it passes through the compressor. This compressed vapor passes to the air-cooled condenser situated behind but outside the refrigerator cabinet, where it is steadily condensed to liquid at high pressure. In the condenser, heat Q1 is transferred from the refrigerant to the surrounding air, which is at a temperature higher than the temperature inside the refrigerator cabinet. The high pressure liquid refrigerant is then throttled through an expansion device before it enters the evaporator as low pressure, low temperature liquid. Actually, after throttling, the refrigerant will be a mixture of liquid and vapor with a high percent of former. To complete the cycle of events, it can be noted that heat is transferred to the refrigerant at low temperature while heat is rejected from the refrigerant at a high temperature and work is supplied to the system. Thus, all the interactions are opposite in direction to those in either the steam power plant or the closed cycle gas turbine power plants. In the type of refrigerator described above, it has been possible to transfer heat from a low temperature region to a high temperature region only because of the work input to the compressor. In the absence of the compressor, it would be impossible to carry out the above heat transfer. This fact embodies the first statement of the second law of thermodynamics. It has been explained earlier that the performance of a work producing cycle is evaluated by its efficiency. However, it is customary to evaluate the performance of a work absorbing cycle such as refrigerator by its coefficient of performance, which is abbreviated as COP, that is coefficient of performance. Similar to efficiency, COP is also the ratio of what we want to what we are paying for. Application of the first law of thermodynamics to the refrigeration cycle gives summation of Q is equal to summation of W. This is the expression for the conservation of energy for a cyclic process. For the refrigerant undergoing the cycle Q2, the heat interactions at the evaporator, what is wanted for providing refrigeration is positive because heat input to the system is always positive. Q1, the heat interactions at the condenser is negative and the work input to the compressor WC, what is to be supplied, is negative. These are all from the sign convention. So we can write the expressions for the first law of thermodynamics for a cyclic process as minus Q1 plus Q2 is equal to minus WC. So Q1 minus Q2 is equal to WC. So coefficient of performance, that is COP refrigeration system, is equal to Q2 divided by WC, and COP of refrigeration system is equal to Q2 whole divided by Q1 minus Q2. Now let us talk about the heat pump. A refrigerator provides a low temperature region by transferring continuously the heat from the region to be cooled to the surrounding at a relatively high temperature. A refrigerator or a window air conditioner, which also operates on a cycle similar to that of the domestic refrigerator, is a necessity in hot climates. In cold climates, it may be necessary to provide a relatively high temperature region like a heated room. It can be achieved by a heat pump, whose operation is exactly similar to that of a refrigerator. Figure 1 is also schematic of a heat pump. In a heat pump, one is interested in Q1, the heat transfer to the high temperature region. To maintain the high temperature region, heat is continuously transferred to it from the low temperature surroundings with the help of work supplied to the compressor. It may be imagined that a domestic refrigerator can be used as a heat pump by installing it in such a manner that with its door open, the cabinet is exposed to the cold weather outside the room and the condenser coil is exposed to the room air to be heated. It is needless to mention again that a heat pump is also a work absorbing cycle. Now for a heat pump, COP of heat pump is equal to Q1 divided by WC equal to Q1 whole divided by Q1 minus Q2. So COP of heat pump is equal to 1 plus COP of refrigeration system. Now refrigerant. Refrigerant is the working substance circulating in the refrigeration cycle. The common refrigerants available at reasonable cost are ammonia, carbon dioxide and Freon 1,2. Freon 1,2 condenses at moderate pressure and under normal atmospheric temperature conditions. This property makes the refrigerant suitable for most refrigeration application. Air conditioning systems, you know very well we need air conditioning system in summer so that we can get the temperature at comfort zone and the moisture can also be controlled and there has to be circulation of air inside the room because of the air conditioning systems, and also the air has to be purified before entering the room. The process of conditioning the surrounding air according to the human comfort and desire is called as air conditioning. Application of air conditioning is that you know very well that in restaurants, hotels, home, hospitals, airplanes, offices, air conditioning systems is very much required in these areas. So air conditioning also helps control moisture in printing press. In business and industry, air conditioning improves efficiency. Manufacturing of tools and instruments, textile mills, here also air conditioning systems are very much required, and pharmaceutical, chemical plants and food industries. Now let us take up a very interesting numerical, that is a reverse heat engine is operating between minus 13 degrees centigrade and 37 degrees centigrade. Find the coefficient of performance as heat pump and refrigerator. We know very well the expression for COP as refrigerator is equal to Q2 by W is equal to Q2 divided by Q1 minus Q2, that is equal to T2 divided by T1 minus T2. So in this case T1 is given as 37 degrees centigrade and T2 is minus 13 degrees centigrade. But while solving these problems, you must convert these temperatures into Kelvin scale. So T1 will be equal to 310 Kelvin and T2 will be equal to 260 Kelvin. Just you add 273 of the respective temperatures. So COP of heat pump, we know very well that is 1 plus COP of refrigerator. For the refrigerator you have calculated COP, that is equal to 5.2. So COP of heat pump will be 1 plus 5.2 is equal to 6.2. Now let us take up another problem, that an ice plant using water at 10 degree centigrade produces 4.8 into 10 to the power 5 kg of ice in 24 hours. Plant is supposed to follow Carnot cycle and works between temperature of minus 5 degrees centigrade and highest temperature of 23 degree centigrade. Calculate the capacity of plant in tons of refrigeration and also power required. Assume ice is formed at 0 degree centigrade and the latent heat of freezing of water is 336 kJ per kg and specific heat of water is 4.2 kJ per kg. The cooling or refrigeration effect per minute equal to heat removed from water. Now, heat removed in cooling from 10 degrees centigrade to 0 degrees centigrade plus latent heat of ice. So, that comes out to be 1.26 into 10 to the power 5 kilojoule. First of all, while cooling, we have to cool the water from 10 degrees centigrade to 0 degrees centigrade. After that, the 0 degrees centigrade water, we have to cool it so that it will be ice at 0 degree centigrade. So for that case, you have to remove the latent heat. So in two parts, we have to calculate the heat removed from water. We know that removal of 210 kJ per minute is equal to 1 ton of refrigeration. So capacity for this plant comes out to be 600 tons of refrigeration. So COP of the plant is equal to T2 divided by T1 minus T2. T1 and T2 are known. T1 for this problem is equal to 296 K and T2 is equal to 268 K. So COP of the plant comes out to be 9.57 and also COP is defined as cooling effect divided by watt supplied. So cooling effect that you have already calculated. So there is COP, you have already know, that is 9.57. So the work supplied W is equal to 0.13 into 10 to the power 5 kJ per minute. So power of the ice plant is equal to 219.4 kilowatt. Exercise 3. Assume that the efficiency of heat engine as shown in the figure is 0.5. If this engine operates as a refrigerator between the same two temperature with the same magnitude of heat and work interactions, what would be its COP? Now we know very well that Carnot efficiency is equal to T1 minus T2 divided by T1, that is equal to 0.5. So T1 minus T2 divided by T1 is 0.5. So 1 minus T2 by T1 is equal to 0.5. So T2 by T1 is equal to 0.5. So T2 is equal to 0.5 T1. Now COP of the refrigerator, we know very well T2 divided by T1 minus T2. So we have already got T2 as 0.5 T1. Put the value in this expression and calculate the COP of refrigerator. For this case, it is equal to 1. Now let us take up the exercise 4. A refrigerator with a COP of 4.0 transfers heat at a rate of 0.5 kJ per second at the condenser. Find the rate of heat transfer at the evaporator and the power input to the compressor. Also calculate the COP if the refrigerator were to operate as a heat pump with the same heat and work interactions. So this is the diagram for this problem. Now COP of the refrigerator, you know very well, that is equal to Q2 by WC. So Q2 is equal to 4.0 WC. So here you see Q1 minus Q2 is equal to WC. WC is equal to 0.5 minus 4.0 WC. So from this expressions we get WC is equal to 0.1 kilojoule per second. So Q2 is equal to 0.4 kilojoule per second. We know that COP of a heat pump is equal to 1 plus COP of refrigerator. So 1 plus Q2 by WC, that comes out to be 5. So COP of heat pump is equal to 1 plus 4 is equal to 5. Now let us take up exercise 5. A refrigeration plant for a food store operates as a reverse Carnot engine cycle. The store is to be maintained at a temperature of -3 degrees centigrade and the heat transfer from the store to the cycle is at the rate of 7.5 kilowatt. If heat is transferred from the cycle to the atmosphere at a temperature of 30 degrees centigrade, calculate the power required to drive the plant. So COP of a refrigerator is equal to net refrigerating effect divided by W, that is equal to Q2 divided by Q1 minus Q2, that is equal to T2 divided by T1 minus T2, that is equal to 7.5 divided by W, and T1 and T2 are known. So from these expressions you can easily calculate W, that will comes out to be 0.92 kilowatt. So we have discussed our today's lecture. Let us very quickly summarize what we have discussed in our lecture session. We have discussed refrigeration system, we have discussed about the refrigerator and heat pump, we have discussed the refrigerants, we have discussed about the capacity of refrigerator, and we have also discussed how to calculate the coefficient of performance. Thank you very much.